And I want to welcome you to the 349th presentation of the Wonders of Physics. What is a number? We use numbers every day. In fact, we use them today to make sure that everyone had a place to sit in this auditorium. Well, lately in the physics department, we've been having, let's say, a lively discussion about what the most important number in physics is. You see, I think it's 273. Before I took over this program from Professor Sprott, I was a meteorologist at a local TV station. So I am well aware how important temperature is in our everyday lives. And in fact, just a small change in our global temperature could have devastating consequences for our planet. So I think 273 is the most important number. Because 175 years ago, physicists discovered that while there isn't an upper limit to temperature, there definitely is a lowest possible temperature. And that temperature is minus 273 degrees Celsius. That's what we call absolute zero, or zero on the Kelvin scale. Now, it can be hard to imagine what absolute zero looks like, but I have a demonstration that might help you out. For this demonstration, I need 5 volunteers who really like to dance. I mean, you really like to move. You like to? Okay, come on in the fuchsia shirt. You want to? All right, come on down. Do you want to dance? Okay, come on down. You want to dance? Yeah, come on down. I think I have 4. I need 1 more. In the Santa hat? You want to dance? All right. All right, come on. Can you guys make a line facing the audience this way? There you go. All right, well, we got 6. No problem. We can deal with 6. You guys are my atom dancers. Atoms are teeny tiny particles. They make up everything. You did? High five, high five. Well, then you know that atoms are always moving. So what should you guys be doing right now? You should be moving. Yes, you should be dancing because atoms are always moving. Yeah, all right. Now, when atoms make up really hot substances, let's say boiling water, they have a lot of heat energy. So what do you think those atoms look like? Even crazier. Yes, you need to move even faster. Faster, faster, faster. All right, perfect. Now let's say you're an atom in an ice cube. That atom does not have a lot of heat energy. What would it look like if it was moving? Slow motion. Yeah, slow motion. Perfect. You guys are perfect ice cube atoms. Now, freeze. This is what absolute zero looks like. They're still breathing, but they're not moving. Everyone give the atom dancers a round of applause. Thank you. So we'll start the show with number 273. Now, I've asked friends from the physics department to come out for us and demonstrate which number they think is the most important. And I think by the end of the show, we might have a pretty good idea of which number reigns supreme as the most important number in physics and maybe even the galaxy. So without further ado, I'd like to... Stop the show! Whoa, wait. Who are you guys and why are you here?
My name is Gavin, this is Raheem, and that's Lael, and we're from the FBI.
The FPI?
That's right, the Fun Physics Institute. And we've received a report that there may be some radioactive material here in the auditorium.
Oh, do you know what you're looking for?
We don't, but we have all of you. Maybe you can help us. Is there anything that you've seen around here that maybe looks radioactive? Point it out if you've seen it. It looks like maybe over here.
Could be that over there.
Could be. Let me think. We'll have to check it.
How do we test it?
Well, we have a Geiger counter here. Here's how it works. In a second, we'll take this probe and place it near a potentially radioactive source. Now, if radiation passes into the front of the probe, it will send an electric signal up into this box, which will then keep an audible count for us. We can hear it of each time the probe essentially feels radiation. Should we try it? Yeah. You did not sound convincing. Should we try it? Yeah. Much better.
I think we found it.
I think so too. Thank you for all of your help. Now, that's a fairly active source, but believe it or not, it's actually quite safe. Inside that small puck is a piece of strontium. Strontium emits beta particles, which we can think of as equivalent to electrons. Now, beta particles only travel about 3 feet through the air, so all of you are well outside of its range. Pretty much the only way this could be dangerous to you is if you ate it, but that would be silly because it wouldn't taste very good. What's amazing to me is that radiation like this is all around us, but we don't think about it because we can't see it. The probe is not near the source right now, but you can still hear occasional pieces passing through, right? A good physics number that you should know is 2 millisieverts. 2 millisieverts is the amount of radiation that you naturally absorb every year, just like that. As an example of something you might be familiar with, I have here a common household item. Who can tell me what this is? That's right, it's a smoke detector. Good job. Believe it or not, a lot of smoke detectors come with a small amount of americium inside. Americium is a radioactive metal that emits alpha particles. It uses those alpha particles to tell whether or not there's smoke in your house. And to prove it to you, we've taken this one apart so you can see. We place the probe there. Radioactive.
FBI, in your professional opinion, can the show continue?
We declare it safe. The show can go on.
Well, we're already here, and there's a ton of cool physics experiments, so why don't we check some of them out before we head out?
Sounds fun. What do you
How
got
about
in
that
mind?
one over there?
Let's do it.
So it looks like here we have a bunch of pendulums, but these aren't just any boring pendulums. This here is what's called a wave pendulum. Should we try it out? Okay, so what we're gonna do, we're gonna set the pendulum up, and we're gonna count down. And we say go, we're gonna release the pendulum and start this timer. All right, let's do it. 3, 2, 1, go. All right, so it looks like here we have 16 balls in total, and each ball is hung on its own string so they can move independently of one another. The lengths of these strings were carefully set up so that when we release all the balls at the same time, they go through this complex dance that can repeat itself over and over. Now, if we keep an eye on the pendulum and also on the timer, what we'll see is that at right about the 25-second mark, all of the black balls are on one side and all the red balls are on the other side. Now, it would be a pretty good guess to say that's the halfway point of our repeating motion. In other words, if we go forward another 25 seconds, when the timer will strike 50, what we expect to see is that all the balls will form back into a straight line, just like they were in the beginning. And from that straight line, they can begin the dance once again. So that was pretty awesome, but I think we should take a look at something else. How about that over there?
Sounds good to me. So it appears this is a machine that generates lasers. But what's a laser? A laser is simply light amplification by simulated emission of radiation, which is just a fancy scientific way of saying a powerful beam of light. And as all light, this light beam also has a color. Let's find out. It seems to be a lightish blue color, which is conveniently the same wavelength as our number for this experiment, 450 nanometers. However, it is a bit hard to confirm this. Can you see clearly what color this is?
I can't really tell what color it is.
Well, luckily, there are quite a few ways to verify the color of a beam. For example, Lael, could you please put the yellow balloon inside the test chamber for me? Awesome. What do you think is going to happen when I press the button? Will the balloon pop or not pop? Pop! All right, let's see. Count down with me. 3, 2, 1. So in science class, we learned that yellow objects reflect the yellow light, which conversely means they absorb blue light. So when we fired a blue light at the balloon, all of the energy got absorbed and the balloon went pop.
So that gives me an idea. What if, instead of a yellow balloon, we put this bluish purple balloon inside of our test chamber and shine the laser on it? What do you think might happen? Gonna pop? Not pop? Got about you got a 50-50 chance. What do you say? Pretty good. Well, let's do a test. Let's see what happens.
All right, once again, let's do the experiment together. On the count of 3. 3, 2, 1.
Wow. So we think, well, why did this one not pop? Well, the color of this balloon is roughly the same color as the light being emitted by our laser. So what happens is the light hits the balloon, and most of it just gets reflected right off. It can't absorb any energy, therefore does not pop. Perfectly safe.
Well, that was kind of anticlimactic. So what if we do one more small experiment? What do you think is going to happen when I put this inside the machine? Let's find out. One more time, everyone. 3, 2, 1. So what's basically happened is that the beam of light passes straight through this transparent balloon, hits the yellow balloon, and as we learned just a few moments ago, the yellow balloon absorbs all the light and pops, giving us this little object. Does anyone want this as a souvenir? All right.
Now, lasers are pretty cool, but how about some rockets? What I have for you are not rockets like those that go to outer space using flame. Instead, these use pressure. And to show you how it works, I've got 100 pre-built rockets right here. On the underside of this tray are a bunch of film canisters. Inside those film canisters is a little bit of water and an Alka-Seltzer tablet. Now right now they're not touching. When we flip this tray over, they'll begin to react. One of the products of that reaction is carbon dioxide, a gas. The catch is the gas has nowhere to go because the lid is sealed. So it builds up pressure until the pressure exerts so much force on the lid that it pushes the canister off towards the ceiling. Now, front row, your signs there. Yes, this is your moments. We expect some of them to land around you. We don't expect you to get wet, but we figured you want to know that they're coming. With that, let's go ahead and get it started.
Like we have about 95 canisters, 96 canisters on the ground. We need the canister control crew out here to pick these up. Canister control crew, can you come out?
We have one more special number to share with you, and that number is 1.5. Why 1.5? Because when you mix 1 part water with 1.5 part cornstarch, you get the oobleck, which is a non-Newtonian fluid. Yes or no? Do you know what a non-Newtonian fluid is? Yeah. Awesome, great. For those of you in the audience who don't know, what makes a non-Newtonian fluid so special is that when I scoop a large chunk in my hand and apply pressure through my fingers, it acts like a solid. But the moment I reduce the pressure, it starts melting, like putty. Let's try something a bit more extreme. So, as I tap dance around, I'm perfectly fine. But the moment I stand still, I start to sink. Slowly and slowly sinking, just like quicksand, which is another type of non-Newtonian fluid. Hang on, give me a second. Well, actually, I'm stuck. All right. Well, it looks like this is my life. But non-Newtonian fluids are actually all around us everywhere, and clearly all around me too. A common one is ketchup. So the next time you have trouble getting ketchup out of your bottle, rather than flipping it over and hitting it, just let it rest and let all the ketchup flow out. And speaking of hits, Hattie, weren't our numbers a great hit? We hope you enjoyed them as much as we did. Maybe just roll me away, guys. All right. Yeah. Don't try that at home.
All right, I'm so glad the FBI showed up today to reassure us that even though there's radiation in this space, we are safe. And they had some other pretty cool demonstrations. The wave pendulum, the lasers, 100 rockets. I mean, 100 is a pretty cool number. In fact, I love it. It's a nice even number. Do you guys know what's odd? Every other number. Now, before the next group comes out, I would love to let you know that if anyone is cold in this space, you can head back to that corner because it's 90 degrees over there. I love a joke that combines weather and numbers. Now, our next group of presenters is the steampunk physicists. Please give a warm welcome to Mitanshu and Asia.
Thank you, Hattie. I'm Mitanshu Thakur, a UW Physics grad student.
And I'm Asia Baines, also UW Physics grad student.
And we are excited to be a part of the Wonders of Physics show focusing on important physics numbers. We feel our numbers are the best. Furthermore, our numbers deal with important years in physics and with the important physical values instead of the numbers often associated with us.
I really hate that picture, and all we do is break a couple of laws of physics.
Yeah, it's not one of your better photos. So let's start with the number 1831. 1831 was an important year in physics. That year, Michael Faraday discovered what is today called Faraday's law of electromagnetic induction. This law further laid the groundwork for the modern electrical world.
In fact, we are wearing our steampunk outfits in honor of that era of the 19th century.
Faraday's law states that a changing magnetic field can actually produce a current in a wire. Thus, we can actually produce electricity just by changing the magnetic field. Now, I will demonstrate this concept using a magnet and a copper coil. So, as you can see, as I am moving this magnet inside the copper coil, a current is produced in this wire, and you can see this on the galvanometer. The important thing to note here is that the current is produced only when the magnet is moving. If the magnet is stationary, no current is produced and the needle is also stationary.
So now, let's demonstrate this principle with this apparatus. I have here a small copper coil with leads attached to this photographic flash bulb. And I have here a strong indium magnet. I'm going to smash this magnet against the copper coil, which will then induce a current, causing for the light bulb to flash. This is very bright, so please don't look directly into the light bulb. Look to the sides or above me, and then we'll count on 3 to set it off, okay? 1, 2, 3.
Oh. Is there anyone that did not take her advice? I'm holding up 2 fingers. Can you tell?
Speaking of light, did you guys hear about the photon checking into the hotel? The bellhop asked if they could help with their luggage, but the photon said, "I don't have any, I'm traveling light."
Now we have another demo for you based on electromagnetic induction, but with a twist. Now I will take this neodymium magnet and hold it above this large copper plate at room temperature. As I drop this magnet, it produces a current in this copper plate, which then produces a magnetic field in the opposite direction, causing the magnet to fall very slowly. Now this copper plate has been cooled with liquid nitrogen to a temperature of minus 196 degrees Celsius or minus 320 degrees Fahrenheit, making it a supercooled copper plate. As I drop this magnet, it produces an even larger current in this copper plate, which then produces an even larger magnetic field, causing the magnet to fall very slowly. Now we can also stand the magnet on its side and tip it over like this. You know, I was reading this book on anti-gravity and I can't put it down.
So now on to our next important number, 14.7. On Earth, the atmospheric pressure is 14.7 pounds per square inch, or PSI. We can imagine the atmosphere like the ocean, but instead of water, it's air. So it's all pretend we're at the bottom of the ocean. You have all this water pushing down on you. Suddenly on Earth, you have all this air pushing down on you from all sides. So take my hand, for example. We have air pressure acting on top of it and at the bottom of it. Thank God or else when we lift up my hand. So now, let's demonstrate how strong air pressure can actually be. I have here two hemispheres called the Magnetism hemispheres. Whenever I put them together, they simply fall apart. That's because the air pressure on the inside is equal to the air pressure on the outside. So let's see what happens when I attach these hemispheres to this vacuum pump and take out all the air from the inside. But in order to do that, I need a volunteer. Hattie, can you please find me a volunteer?
I would love to help you out. So I think Asia needs someone who's really, really strong, can pull these apart. You want to try? Yeah? All right, come on down. Yeah, what's your name?
Ajax.
Ajax? Ajax, how old are you?
9.
9? 9-year-olds are known for their strength, right? Yeah, all right, come on right here. Just stay right here. They'll come to you, okay?
Okay,
Yeah. Are you ready? Did you eat your Wheaties this morning? Okay, good.
Okay, Ajax, I want you to pull that as hard as you possibly can. Oh, okay. I guess we'll start now. Go, pull as hard as you can. Pull. Okay, this is obviously not coming apart. So what do you think we could do to get these hemispheres apart using physics?
You could let the air pressure out.
Yes, you could add air back in. Okay, so when you hold that side, Matanshi, can you please open the valve to add air back in?
Sure.
Oh, they came apart! Everybody give Ajax a round of applause. Okay, as you all saw, all we need to do is just add air inside. That's because the air pressure on the inside was 0, so all the air pressure on the outside was acting on these two hemispheres, causing them to be stuck together. As you can see on the slide, the diameter of these hemispheres is about 5 inches. So, Ajax and I both need to have about 300 pounds in each arm in order to pull these apart. And I don't know about you guys, but I know I'm not that strong.
Now we have another demo for you, but for that we will need a volunteer. Now Hattie, can you help us find another volunteer, please?
Sure. Let's switch it up this time. Is anyone celebrating a birthday today? I have like 5 people have the same birthday? You have a birthday? Okay. No birthday today. Birthday this week? Is your birthday this week? Okay, come on down. I was really impressed with the 5. What's your name?
Sawyer.
Sawyer, when's your birthday?
February 24th.
February 24th, so that's coming up, just about a week away. Awesome. How old are you going to be?
I'm gonna be 12.
12. Okay. Well, we are lighting candles.
Can I borrow that?
We've got 1 lit for you right now. We're going to light a total of 5. Why don't you go back here? Just for your birthday, okay, Sawyer?
Okay. So you can take a stand over here while I light these for you real quick. So we're gonna light these candles in honor of your birthday. And if Matanshi, if you can hand me the beaker, please.
Sure.
Thank you, Hattie. Okay, so we have here an empty beaker, and I want you to pour down the trough as if there was water inside, okay? Okay, you got this. Whoa! How did you do that? Let's see if there's more in there. Yeah, just go. No? That's okay. Okay, perfect. Okay, so the beaker had not water inside, but carbon dioxide gas. And carbon dioxide gas is denser than air. So when you pour down the trough, all the oxygen and air needed for the candles to continue burning went out. So happy birthday. Let's all give him a round of applause, and here's a sticker. Take both. Okay, since our demos deal with atomic structures and elements, did you guys hear about the neutron that got arrested? They're released without charge. So fun.
Now for our final demo, let's boil some water.
Okay, who knows what the boiling point of water is? Just shout it out. 100? Yes. Yes, exactly. Okay, 100 degrees Celsius or 212 degrees Fahrenheit. But there's a qualifier with that. We need to be at sea level, or as I mentioned earlier, at 14.7 psi. As you can see on the screen, Madison is about 700 feet above sea level, so we need 210 degrees Fahrenheit in order to boil water. For Denver, Colorado, the Mile High City, 203, and for Mount Everest, 160 degrees Fahrenheit.
So let's start by taking this flask of water, okay? Now just to ensure that I'm not deceiving you all, I want someone to check the temperature of the water inside the flask. Can you check the temperature? Does this feel hot?
Nope.
It's at room temperature, right? Now I will connect this flask to this vacuum pump and pump all the air outside, thus lowering the air pressure. Watch what happens. As you can see, the water inside the flask is boiling, but I am not adding any heat to it. Now I want you to check the temperature of the water again for me. Does this feel hot?
No, it's the same.
It's the same, right? So we actually boiled water not by adding heat, but by lowering the air pressure and thus lowering the boiling point to the room temperature. Isn't physics amazing?
So with that, we conclude. As you can see, our numbers and values give a fuller understanding of our physics demos. Don't you think our numbers were amazing?
But our demos were the best, right? Thank you.
Thank you.
Thank you, steampunk physicists. Thank you so much. We got a history lesson. They connected electricity to magnetism. They extinguished the birthday candles with a seemingly empty beaker. Pretty amazing. It gets me thinking, did you guys know that in any group of more than 23 people, there's a greater than 50% chance that at least 2 people share the same birthday? Yep. Hard to believe, but the math works out. If you're interested in seeing a step-by-step calculation of that math problem, you can scan that QR code and it'll take you to the answer. Well, I'm hungry for birthday cake now, and maybe you are, but we need to move on with the show in our quest to find the most important number in physics. Our next group, the grad students, you may recognize some of them from last year. Please give a warm welcome to Sam, Owen, and Braden.
Guys, I've been telling you all week that my number is the best, and I don't know how you can even contest that because it literally comes first in the natural numbers.
Hey guys, what's happening here?
Hattie, maybe you can help us out. We're trying to decide who among us has the most important number.
Me.
Well, I think you guys can all make your case.
Okay, so my number is the best because it comes first in the natural numbers. It's like very singular. Like, I don't know how you can avoid that.
One at a time.
Okay, Hattie, I think that's a great idea, since the audience will clearly choose my number.
And which number is that?
5.67 times 10 to the minus 8.
What?
5.67 times 10 to the minus 8.
That's terrible.
Nothing that's important should have that many digits.
It's the Stefan Boltzmann constant.
You know, that's nice and all, but why should anyone care?
Because we wouldn't be here without it. The Stefan Boltzmann constant is used in the law that describes black body radiation. Any temperature, or any matter that has a temperature above absolute zero, has atoms move back and forth, just like we saw in the demo earlier today. As those atoms move back and forth, they release electromagnetic energy in the form of light that then gets radiated away from the source. This is how we get energy from the sun. This is why we have life here on Earth. And this is what I'm going to use today to work on my tan.
Expecting to get some sun soon?
Yeah, I'm hoping to get in a beach day sometime this week.
A beach day. In February. In Wisconsin.
Yeah, maybe not this week, but we can still get some of that light energy in over here. What I've had heating up over here is a coil of wire, and some of you can see that it's orange. It's super hot, and all that light is getting radiated away from it, all that heat. And there's also some invisible light, that's infrared light that you can't even see as well, that's also being radiated away. And so what we're gonna do is collect all that energy with this parabolic mirror here and focus it into a beam, just like a car headlight, and direct it all the way across this room into this other parabolic mirror, where we'll then refocus the light onto a match that I have hidden here underneath this curtain. Now, Do we want to see what happens when I lift up the curtain? Yeah? All right, are we ready? 3, 2, 1. See? Can't get that without the Stefan Boltzmann constant. Plus, it's super easy to remember. 5, 6, 7, 8.
Aren't you missing a times 10 to the negative in there?
Well, yeah, that's implied.
Sure it is.
Okay, well then why don't we tell us what your number is?
1.
Just one?
One what?
Just 1. I think most people can agree that 1 is a pretty big number. Bigger than average, really.
Yeah, okay.
In all seriousness, I mean 1 ATM, or atmosphere. It's the pressure of the air around us here on the surface of the Earth.
I don't feel any pressure right now.
The only pressure I feel is for your number to do better than mine.
Well, even though we can't feel it, we can still see its impact. There's enough air getting pulled down by Earth's gravity to weigh about 14.7 pounds per square inch, which you heard earlier. That's like getting crushed by a full-sized car all the time. Now, as you can probably tell by how jacked I am, I've been hitting the gym a lot lately and I've gotten pretty strong. You see this can over here? I'll bet you I can crush it with my bare hands.
Yeah, sure you can.
Be skeptical all you want, but it's true. I'm just gonna use that atmosphere of which you two seem so wary. Now, as you can probably tell by the steam coming off here, I put some water in here earlier and now it's starting to boil. So what I'm gonna do is turn off that heat, and I'm going to seal up this can. And like me after a good workout, I need to cool down a bit. So what I'm going to do is I'm going to give this can a nice cold ice bath over here, and then you'll see just how strong I've gotten. So let me limber up a little bit, stretch it out. All right, here we go. You guys ready for this? I'm going to crush this can. All right, here we go. Come on. Gotta really lift with my back, or my legs, not my back. Come on. Oh, gosh. Oh, oh, God, I'm really strong. Whoa. Working up a sweat over here.
Yeah.
Wow, that was pretty impressive.
I know. Now, I might have cheated a little bit. So, when I had that water boiling, it was building up water vapor on the inside, which created an outwards pressure pushing against the atmosphere, which was pushing inwards. But then when I dunked it in the cold water, that water vapor condensed back down into a liquid, causing the pressure to drop, and then the atmospheric pressure wins, causing the can to implode. So yeah, while 1 ATM might not seem like a lot, it's a lot stronger than we are.
That's cool and all, but you definitely cheated.
Yeah, the audience is never gonna fall for your lies and your deceit.
Excuse me?
Now, I'll admit, you guys have some, pretty cool numbers, but I'll bet you they don't even hold a candle or a match to my number.
Yeah, and what number is that?
Earth's gravitational acceleration, 9.8 meters per second squared.
That doesn't seem very important to me.
Now, I think you both are underestimating the gravity of the situation. Tough crowd. But in all seriousness, this number is the reason why we're even on the ground right now. Without it, we'd be floating around, and a simple jump could send us flying off into outer space. This number characterizes the rate at which objects fall back to the Earth. So, whenever I go for my skydiving lesson later today, for each second that passes, my speed towards the ground will increase by 9.8 meters per second, or roughly 32 feet per second. I don't know about you, but that's pretty fast. So whether I throw a baseball up into the air or my friend Sam over here, they'd both fall back to Earth at roughly the same rate. If there wasn't any air resistance due to pressure, but
See, my number is better.
Let's not get ahead of ourselves, all right? You may think that you're strong, but I assure you that gravity is much stronger. And to demonstrate, I will try to beat gravity with my very own rocket launch. And here is my rocket.
That's a rocket?
Well, an actual rocket wasn't quite in the budget, but this jug will do quite nicely. Inside this jug, I have a highly flammable liquid called ethanol that has been building vapors inside this jug since the beginning of the show. Now, I don't need much of this excess liquid, so I'm just going to dump some of this out over here in the sink. And I will take this handy dandy little cable and attach it to this piece of copper that I have sitting in the mouth of the bottle here. Now, I will be igniting this using a handheld Tesla coil. And for those of you that know, a Tesla coil will cause electricity to arc to nearby pieces of metal, like so. I think without further ado, it's time that we go ahead and light this, right? All right, 5, 4, 3, 2, 1.
That went really far.
Yeah, I can hardly make it out from all the way over here.
Yeah, ha ha ha, very funny. While my rocket launch may not have been as successful as I had hoped it would be, this just goes to show how strong gravity really is and why my number is the best.
Yeah. Okay, I think it's high time that the audience finally got to decide whose number was really the best. So if you thought that my number, 1 ATM, was the best, the strongest, which it obviously was, I want you to give me a big round of applause. Yeah, thank you. Come on.
And if you think my number, 9.8 meters per second squared, was the best number, clap your hands.
Okay, but if you thought my number, 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the 4th, was the best number, give me a round of applause.
Great demonstrations, but I don't know if we can determine a clear winner just yet. We're gonna have to keep looking.
Come on, my number is literally number 1.
My number was
It's literally the best.
Now, we've seen some pretty big numbers so far in the show. It can be hard to wrap your brain around it, but you can maybe think about it this way. 1 million seconds is equal to about 12 days. But 1 billion seconds is equal to more than 31 years. So there's the difference between a million and a billion. And looking at my watch, we have about, carry the one, 1,600 seconds left in the show, and I don't want to waste any of them. So I'm going to bring out our next group. We can always count on Emeritus Professor Winokur for a rational presentation. And this year, he's joined by his twin Gary, who's actually just returned from outer space, where he was researching the nature of quantum entanglement. So please give Professor Winokur and Gary a warm welcome.
Thank you, Hattie. But sadly, it's been a difficult reunion. We were in our prime when I left, but look at me now. I suppose it's just a sign of the times and the consequences of Einstein's special relativity.
Stop it. Just me now, Michael. No, folks, it's not my glowing skincare routine. You know, it's just time has really been slowing down for me when I've been traveling at speeds close to the speed of light.
But you look pretty good. So I hear that in the vacuum of space, no one can hear you scream.
That's right. Do you all want to know a secret that's just out of this world? Some explosions are actually noiseless. So to demonstrate, we have this little jar with a bell inside, which you can easily hear ringing when I hold it close to my microphone. Can you all hear that? Now let's see what happens when we remove all the air from the jar using this vacuum pump.
All right, I'll turn it on. It's pumping down. The needle tells us how good the vacuum is. When it's down to about 2, it's good enough. We've removed almost all the air. And I think we're there. Okay, let's close her up and turn it off so you can't hear anything.
Can you hear it now? Of course not. So no air means no sound. Well, that sucks. Now, let's see what happens when we let the air leak slowly back in.
That That was very nice, Gary, but shouldn't you say something about the research we were doing in terms of quantum numbers and quantum entanglement?
Sure thing. So since we're entangled twins, watch what happens when I do this.
Ow! Hey, stop that for the last time. But does that really explain quantum entanglement?
Well, maybe just a little bit. Quantum entanglement is all about two things that are connected even at large distances. Einstein called it spooky action at a distance.
So I suppose we can try it. Did you bring the quantum entanglement dice?
I sure did. So these dice here are called quantum dice with quantum numbers. So the white die is mine and the black die is Michael's. They match us. Now, they're quantum entangled because they're connected by this long, rigid rod, and the two numbers always add to 7. It's my lucky number. So I'm going to give it to Michael. I'll close my eyes and you can give it a whirl.
Round and round she goes. Where she stops, nobody knows. And I'll just peek at my die and be quiet because we don't want to give it away. And I can see my number, and because of the entanglement, I know what my twin will say when he sees his number. It's this one. Okay, Gary, take a peek.
All right, so I can see that my die is 2. So that means I know my twin must have rolled a 5.
Very good. Now, individual numbers on their own aren't always important, but how they move through space and time. So over here we have another device. Perhaps you recognize it. Just call it out.
Tuning fork.
Boom, yes, it's a tuning fork. We actually have 2 tuning forks. They're similar and they ring and vibrate at close to, but not the same frequency. We call them almost twins.
Now, my tuning fork will vibrate back and forth 440 times each second. It's a note A4 on the musical scale.
Now mine is similar, but it's been modified, altered. There are 2 little masses on the arms, and so it will vibrate at a slightly lower frequency at 438 hertz or cycles per second. Let's listen to it. Now, I don't know about you, but I can't really tell the tones apart.
So you might say that there's not a whole lot of difference between these 2 forks, but they bring something to the table when we strike them together.
Ready, set, go. Do you hear that? Do you hear the new sound? Woo, 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 yeah? So we call that a beat. And what's happening is fairly simple, but as you listen, the 2 tones are in sync or in phase, and then a little later they are out of sync and out of phase, and that's when it gets soft. That difference is about 2 cycles per second, or 2 hertz. That's the beat frequency, and that's the difference in the frequency between these 2 tuning forks. How sound waves add and subtract also depends on the physical space in which they move. I want to bring your attention over here to this long copper tube. It's called a Rubens tube, and it will show you what a one-dimensional superposition of sound waves sounds like.
So at one end of the tube, we have this loudspeaker, which will play sound at 1 frequency. Now that sound will go to the end of the tube and reflect back. Now these traveling back and forth sound waves will either add constructively or subtract destructively. And at certain frequencies, they'll form standing waves, which you can see with your eyes.
Wait a minute. Wait just 1 minute. How do you expect your audience to see sound waves?
Oh, didn't I mention? So our tube is filled with methane or natural gas. It also has 350 holes drilled along the top. That's 2 times 175. Now, these holes will leak out a whole lot of gas.
Oh, I don't think so. I don't know about you. I can't even see methane either.
Oh, you can't see it now, but I certainly can see it, especially if I set this gas on fire. I promise I'm not just talking hot air. It's science.
We have to wait a second for the flames to work down. There they are. I think it's getting warm in there. Oh yeah, it is definitely warm. You may be able to see it. It'll get a little better. Blow. And then we'll just turn on the speaker sound, and you may see the standing wave, or the attributes. Let's turn up the amplitude. There, you might see. There it is. Some places it's high, some places it's low. Maybe we could try a slightly different frequency and get a little different standing wave. Well, that's a nice one. Would you like to see another one? Let's try a little lower. Let's see if we can get... There's a good one. Now, the physics is a little counterintuitive, but inside, the methane molecules are moving back and forth. And there are regions where the methane is moving the fastest. Those are called the nodes, and the pressure is lowest. Let me turn the amplitude down a little bit. There we go. And then in the regions where the gas molecules are moving the slowest, the pressure is highest, and so the flame is biggest. Those are the antinodes in this case. Now, the distance from node to node, or antinode to antinode, is half the wavelength. So if I go 2 nodes, I get the full wavelength of the sound wave you're hearing right now.
Now, if you take that wavelength and multiply by the frequency put out by the speaker, you'll get the speed of sound in methane about 450 meters per second. For room temperature air, the speed of sound is 343 meters per second. And for sound, that is the most important number. Now, standing waves can be formed in 1, 2, or even 3 dimensions of space.
Gary, here he goes, counting again. Okay, well, for 2 dimensions, we have another demonstration, and it is called a Chladni plate. And it's a fairly simple device. It's a square of aluminum sheet metal, right here, and it's been painted black. Now, you need to be able to see the consequences of the standing wave, so I have a little shaker here. And what you see, well, it's not salt. This is not Margaritaville, let me tell you. But it's sand, and that will really help when Gary turns on the sound.
Look at that! The sand is actually piling up at places where the plate isn't moving, or the nodes. Now let's try a different pattern. Pretty neat, huh? Want to see another pattern? Yeah. All right, let's go for another.
Now, this demo emphasizes the nodes where not much motion is there, so it can accumulate. But the real action happens at the antinodes, where things are moving their fastest and the physical forces are the greatest. We will exploit that fact in this next demo, in which we have a 2-beaker leader. A 2-beaker leader. Let's try 2-liter beaker. Say that 10 times fast. And a high-power speaker. Now, just like the tuning fork, a beaker has its own special resonant frequency, which you can hear. This one, let me hit it. You hear that? Okay. Now we have another one inside of the box here, and it's been tuned to a very special frequency.
Now, if we get the frequency just right, that will be all we need for something very interesting to happen. We've tuned this speaker to exactly 503.8 cycles per second.
Okay, so let's turn on the sound. And you can see the consequences of being in resonance between the speaker and the beaker. You can see the straw moving back and forth and that little piece of paper vibrating. But watch what happens when we crank up the sound. Breaking the beaker, way better than my toe.
Sorry, but actually not sorry about that.
Yes, but I have to admit, we've yet lost another beaker in the advance of physics. And from that sound, I can tell our time is at an end. We promise we will be back next year.
And you can count on that.
Thank you, Professor Winokur and Gary. Some sound demonstrations indeed. I think you will agree. Now, I have a riddle for you. A farmer had 30 chickens and 28 cows. How many didn't? 10, yes. It's a little play on words there. 20 of those cows ate chickens, 10 did not. One more. Do you know what the moon and a dollar have in common?
They both have 4 quarters.
They have 4 quarters. You're right. And now that you're thinking about space, I think you'll like the demonstrations from our next group, the Space Cadets, who think their numbers dealing with space are the most important numbers in physics. Please welcome Mace, Allie, and the Count.
I am the Count.
Wait, I was expecting that little guy from the TV show.
Oh, you mean the one with the pointy ears and the pointy teeth?
Yeah.
No, he majored in integer mathematics and early childhood development. I'm into physics.
Awesome. Thank you for clearing that up. Please proceed.
Look, I have 2 balloons. 2! But what is inside the balloons is not the same. One thing is not like the other. What do you think we have in balloon number 1? 1! What? Helium. Very good. Helium is number 2 on the periodic table of the elements, which means that helium has less mass than all the other elements that come after it on the table, including the hydrogen or the nitrogen and oxygen in the air around us. Helium has 7 times less mass than the air. 7! A balloon filled with helium weighs less than an equal volume of air. So the balloon, it rises. Now what do you think will happen if we try to light the helium on fire? Let us find out. This is my favorite part of the show. Counting backwards. Und in 5, 4, 3, 2, 1. So, did the helium light on fire? No. That is because helium is what they call a noble gas. Noble gases are gaseous chemical elements that do not react easily with other elements, which is what happens in a fire. So, no reaction, no fire. But wait, we still have 1 balloon left. What do you think is in this balloon? Oh, hydrogen, very good. Hydrogen is number 1 on the periodic table of the elements, which means it has even less mass than the helium. Now, what do you think will happen if we try to light the hydrogen on fire? I'll give you a clue. You had better cover your ears. Und in 5, 4, 3, 2, 1. One big kaboom. The hydrogen reacted very quickly with the oxygen in the air. In fact, Hydrogen is the best rocket fuel we know of. Thank you all for your attention. Now I would like to introduce you to my colleague, Mace Bishop.
Hi, everybody. So, you know what I think is a pretty important number in physics? 77 Kelvin, which is the boiling point of liquid nitrogen. Now, 77 Kelvin is just 77 degrees above absolute zero. So this stuff is really cold. And in fact, it freezes just about everything it touches. Now, I have here a balloon that's been filled up with air from this room. Okay? Now, if you remember from the beginning of the show at the atom dance, molecules with a lot of energy move around really quickly, right? And these air molecules are warm, so they're doing that. When they move around on the inside of this balloon, they smack into the walls of it and hold it open. That's what creates air pressure. So what do you think will happen when I dip the balloon in the liquid nitrogen?
One big kaboom.
Let's find out. So you can see that I have the end of the balloon clipped off, so none of the air can enter or exit the balloon. But it's still getting smaller. The reason for this is that when the air molecules lose energy, they can't move around quite as fast, and they can't hold the balloon open so much. But none of the air has left the balloon. If I pull it out of the nitrogen and I hold it up against something warm, it should reinflate. All the air is still in here. One of the ways that this is relevant to space is the concept of cryosleep. Space is really big, so sometimes getting from place to place could take years. But if you could freeze yourself in just the right way, you wouldn't have to be awake for that whole journey. So they won't let me practice on real animals just yet, so I have this balloon animal that we'll use as an example. If I put it in this larger tank of liquid nitrogen, if you're up on the top row, you might be able to see this, but this balloon animal will shrink too. There he goes. Okay, check him out. But if I just let him warm up a little bit, he should go right back to normal. Look at that. Oh, looks like he has some friends in there. Oh my gosh, puppies. Well, it looks like it's back to the drawing board with my research. Now for a demonstration from Allie Man.
You might want to work on your thesis some more.
Yeah, absolutely.
Thank you for the introduction, Mace. My name is Allie, and I'm a first-year PhD student and space cadet here at the University of Wisconsin-Madison. Now, we've seen a lot of really cool numbers today, but arguably, I think the best number has to be the speed of light. It has a value of 300 million meters per second, which is 2.29 million times faster than a Ferrari F40. We use it to transmit data, see, and it's the speed limit of the universe. It's so effective at transmitting data, in fact, that we use it in NASA's Deep Space Optical Communications experiment in order to transmit data from over 10 million miles away just using lasers. But me personally, I like to use it to listen to my favorite tunes on long space flights. So to demonstrate that, in front of me I have an ordinary laser pointer. We can see it using a bit of canned air that I have here. It's the kind of laser pointer that you might use to play with a cat. Now, all the way over here, I have an ordinary photodetector or solar cell, kind of like the type you might find on top of a rich person's house. And connected to it is the speakers in this room. If you pay attention closely, you can hear the humming from the laser pointed at the photodetector. And if I interrupt that signal, we should be able to hear it. So I'll just go ahead and pass my hand through now. Isn't that cool music? What's happening is the laser is flashing on and off very quickly at a frequency that we can interpret when it's sent to the speakers in this room. I can even transmit the frequency of something like a tuning fork to the laser. So if I place this in front of the laser, we should be able to hear it. it's not exactly the kind of sound I want to listen to on long space flights. And I don't think many of you would like to listen to that either, right? So who wants to listen to some music? You can be a little more excited. Who wants to listen to music? That's more like it. So I'm going to go ahead and connect the laser to my space data pad here, and it'll flash the light on and off very quickly at the same frequencies that the song is playing at. And since everything's better with a countdown, I'll turn music on in 5, 4, 3, 2, 1. I can even turn myself into the world's worst DJ. So music off. Now how cool is that? So if anyone asks you what the best number in physics is, you're going to tell them it's the speed of light.
Thank you, Space Cadets. Your demonstrations were out of this world. Thank you so much. Give them a round of applause.
Hey, Hattie.
Yeah. Oh.
Hattie.
Hi.
What a great show. However, I think the best number is 73.
73?
73 is a 21st prime number, and its mirror 37 is a 12th prime number, whose mirror 21 is the product of, hold your hats, 7 and 3. Furthermore, 73 in binary is a palindrome, 1001,001, which backwards is 1001,001. 73 is also a palindrome in Morse code, da 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 da, and it's used to mean best regards because of its musical sound. Also, 1973 is the year I joined the faculty. But anyway, it's great to see you all. Thank you for coming, and 73.
Thank you, Professor Sprott. So we've seen a lot of numbers today, and it's obvious scientists don't always agree on everything. But we do try to support our theories with experiments and observations. But most importantly, data drives decisions. And any good scientist must be willing to change their mind in light of new evidence. So that is why in this year, I think 175 is the most important number. You see, 175 years ago, our great university was founded, and this physics department has been at the forefront, leading in the measurement of many of the numbers that we've presented today. So in honor of the demi-semi-septennial, I'd like to do one last demonstration. I'll make a cloud. Now, normally we use 25 liters of liquid nitrogen to make our cloud, but I wanted to connect this demonstration to the 175th anniversary. So, while 175 liters of liquid nitrogen would be amazing, safety first. It's not practical in this space. But 175 cups is. And it turns out 175 cups is exactly equal to 42 liters. So maybe that book, The Hitchhiker's Guide to the Galaxy, was onto something, because 42 is the answer to everything according to that book. So in this container, we have 42 liters of liquid nitrogen. Now, as you've learned throughout the show, it's very cold, negative 320 degrees. Now, I'll force nitrogen air into the bottom of the container. That'll push the liquid up into this bar where we have several dozen small holes drilled. As that cold liquid nitrogen comes out of the bar and into contact with the warmer air, the water vapor in the air will condense into tiny water droplets that we call a cloud. So for the 349th time, I want to thank you for coming to the Wonders of Physics.